I'm gonna go get started with this. Um, so last week we started looking at just a couple new functions real quick as far as review is concerned. And it was something you see in college algebra. So exponential functions is where I began. Today we're going to jump into logarithmic functions. Now, the whole focus of it, of course, is, hey, yeah, I need to be familiar with these functions from the perspective of knowing what the graph looks like, how the domain and range look like. And we'll definitely make sure to review that when needed. But we jumped into taking the derivative of stuff, right? So remember, last week we looked at the derivative of an exponential and we used the limit definition to help us here. Today, we're going to look at logarithms as well, but I had a couple here that we wanted to practice as far as just making sure we know how to get the derivatives. So if we're looking at here, trying to find f prime of x, what did someone make sure that they used to find this derivative? Power rules involved, right? Because we have an x cubed. Huh? The product rule is needed, right? We have this and this as separate factors, right? So remember, as we deal with this, it may not be said there, but this is multiplication. We definitely need the product, okay? Well, the product rule tells us do first times derivative of second. What's the derivative of e to the x, though? All right, so this is one of the things that you definitely want to be careful of, which means whenever you're dealing with the derivative of an exponential, always watch for the chain rule, okay? And we'll see that on the second one. I kind of added a little bit more too. So always watch for your chain rule. But then we're going to have the second times the derivative of the first. With the 15x squared, where it's coming from. All right, so keep in mind what we're seeing here is the product rule, first times derivative of the second, second times the derivative of the first. As far as cleaning this up, there's a couple things here, I would try to write both terms in the same order. It does not change the problem much though when you do this, so understand I wouldn't necessarily be too picky with this problem when it comes to the quote unquote simplifying. The one thing that can be beneficial, and we're going to need it moving forward, though, is to get it into a factored form. Okay, this one's not as bad as it seems, though, when it gets to a factored form. Some of the other ones we've dealt with, though, would be pretty tedious, right? Some of those polynomial ones we ran into. But make sure you see here, this one isn't as bad because, hey, they both share 5, so we can pull out a -5. They both have x, pull out 2 of those, and they both have e to the x. So we can factor all that out and just make sure to do the division to get what's left over. The reason we like that, though, is now we have 3 different factors that we can use moving forward to find something, say like a horizontal tangent, like the next problem's asking. Okay. What you'll find here, though, is that we would end up having a horizontal tangent possibly at each of these factors. Okay. We're okay with the product rule, though, and then reviewing the derivative of e to the x here. That makes you understand, though, from the, if I just say to differentiate, this part here is exactly what we're trying to find, okay? Here, we're asking for horizontal tangents. Some of the problems we're going to look at as we go throughout this week are going to start focusing on, let's find not just any derivative, but specific derivatives, right? Especially when that slope is 0. Definitely one of the things we want to find, okay? So getting to this next step, that's where we're going to want factored forms, okay? Any questions with the first one, though, before we go look at the second one? All right. Now be careful here with this one as far as doing the derivative. As I mentioned before, just watch the chain rule. The nice thing about this, though, what is the derivative of x? This is 1, okay? The derivative of e to the x is going to give us the same thing back. But the part you have to be careful of with any function, of course, not just these, is just always double check, hey, what's going on the inside? So here is, hey, there was an exponent there that was 2 to the x. It's not just x right now. So I need to go look at the derivative of that 2 to 2x. So the derivative of 2x, hey, that's just 2. So it doesn't change it too much. All right, so make sure you see we're doing the derivative of each of these terms separately, right? So that's where we're getting this from. But remember, whenever you deal with derivative of e to any exponent, so if I just say e to the g of x, let's not use g of x. Let's use u of x, just to make it different, okay? What you have to make sure to understand that, yes, it's going to be e to the u of x, but it's got to be multiplied with the derivative of that whatever that exponent is, okay? So I copied down e to the 2x here. But we definitely want to do the derivative of that with being multiplied afterwards. So that's where that 2 comes from here. Does that help? Exponential functions sometimes can be a little trickier. Sometimes you might overlook it, especially if it's just 2 to the x, but that 2 definitely makes a big difference. So we have to be careful. With that said, though, is that all we wanted to find here? We wanted to find horizontal tangents, right? So what does that tell me I need to do with what I just found? Set it equal to 0, right? We did all that work to say, hey, when does the derivative function equal to 0? Now, this isn't necessarily a nice equation to solve, okay, but this is going to bring us to something that we're going to talk about today. Okay, as we talk about exponentials, something closely connected to exponentials is logarithms. So we definitely want to make sure we're comfortable in reviewing that. Go ahead and add the 2 e to the x both sides, divide both sides by 2, and guess what I forgot, y'all? Yeah, it's supposed to be 2x, sorry. If you wrote down what I wrote down, make sure you fix it. So when solving things that have exponents involved, we looked at a couple of problems last week that were nice because it was 1-to-1. This is definitely not an example of 1-to-1 though. So this is one example where we need logarithms to help us get to a solution. Now, as far as what a logarithm is, we'll talk more about that when we get to what we call integration. Okay. What you'll find is there's functions out there that can only be defined certain ways, and the natural log is one of those that can only be defined as an integral. So for us, we just kind of have to take what we were taught in college algebra and say, hey, this is what we know to do with it. Okay. So make sure you see here, what we're going to say is let's take the natural log of both sides of this equation so that we can deal with that e to the 2x. Now, we definitely want to do this though, because we're getting to something that actually gives us a solution. So we definitely want this. What you'll find is over here, we'll just put natural log of 1/2, but on the other side, this is where the inverse property that exponentials and natural logs share, since they're both base e, that kind of undoes each other. It's kind of like having a square and a square root together. Okay, it's one of the things you want to remember. But at that point, all we can do is divide both sides by 2 to get to our solution. But you're going to find that this would be a situation where if I needed the value, I'll just approximate it to get what we need. Okay. It is one of those irrational results that I'm going to keep it in this form until I need to move forward with it, right? If we're dealing with an application problem that wants a specific value, let me make sure I round as the application problem wants me to round. Are we okay though with review? I know it's quick review now, getting from here to here, especially dealing with the natural log. All right. So that's kind of the first introduction, right? As I deal with exponentials, remember exponential and logarithms have a special relationship with one another. Okay. Are there any concerns with setting it equal to zero though to get a horizontal tangent here? Now, the fun part is we would have to go in and find more to get the horizontal tangent line itself, but we were just trying to find the x value. So this is all we needed right now. If I asked you to find the line that is tangent at this point, that would not necessarily be as nice here because we have an irrational slope. Okay, but this would be the x value that we're looking for. Okay. Not an irrational slope, sorry, an irrational x value. The slope is zero. Any questions or concerns before we go look a little bit further into the natural logs? All right, so one thing I do want you to make sure you're comfortable with is make sure you go over your properties of logarithms. That's definitely going to be something you want to be comfortable with. It's going to help you in different situations. And there are going to be times where you need to know your properties. So make sure you go through when you're familiar with those. What page of the book? I'm trying to remember. I closed out it earlier. Sorry. This comes right out of the textbook though. So they have this in there if you want a more complete list. I chose this one though, because as you can see, the base is A. So it could be common log, natural log, or any base that we're working with, okay? But you definitely want to make sure you're comfortable with your properties of logarithms. Now, one of the things here though that, as you saw, we talked about is the inverse properties of logarithms. So if I look at something like, hey, a to the log base A of m, that will equal m. Or you could have it as like, say, log base A of a to the m, that'll also equal m. The key you have to watch there is, hey, what do the bases say? Are they the same or not? And we just used that with the natural log a second ago. So make sure you also have in there that, hey, if I see the natural log of x, that's the same as saying log base e of x, but we'll never write that because we're always going to put the natural log. Now, the reason I write all that is I want us to differentiate the natural log of x, and we haven't talked about it, okay? As far as dealing with it from a differentiation standpoint, it's definitely a tedious one to have to go through and deal with from the perspective of the difference quotient. Right? If you just kind of take a quick glance of the difference quotient, this would be the natural log of x plus h minus the natural log of x all over h. Okay. And we can go through here and try to deal with this, but really what you end up having to do is like your log properties and such. And it gets a little messy, especially with some of the techniques that we're going to have to use. And that's not the point of it. I used it with the exponential though, because it was well within our range to simplify and just do a plug-in to check the limit. Remember, that's what we did last week was just pull it up instead of just saying it. Once we plugged it in, we were able to simplify to get e to the x by itself. And even though this limit wasn't as nice to work with, by using just a table approach, we found that, hey, this is definitely going to approach one. Okay, so that's definitely something that was possible for us to work with. All right, we can get through this one, but let's save some time and use a different approach. Okay, and the approach that I'm going to use is just keep it in its notation as y equals the natural log of x. And you could keep f of x if you want. I think the textbook kept it as function notation. Now, we may not have talked about the derivative of the natural log yet, but we have talked about the exponent side, right? The exponential. So what we can do here is say, hey, let's exponentiate both sides of my equation. So let's take it and make both sides exponential expressions, but with a base e. Where the y was, we're just gonna have e to the y. That's just all it's going to be. Make sure you see over here, though, this is going to give us an exponential and natural log together where both bases are e, so that's just going to equal whatever the argument was. So in this case, x. That's where these properties definitely come in and as being helpful as far as solving equations and as even here, just kind of rewriting stuff. Now, the reason we like this, though, is now I have an exponential instead of a natural log. So we can differentiate this on both sides. So let's go over here and say, hey, let's take the derivative of this. And I'm going to take the derivative of this. The derivative of x, though, as we just talked about, that's going to be just 1. The part we do have to be careful of, though, is it's e to what variable? It's y. Y is not an input variable, but it's our output variable. So make sure you see here, yes, the derivative of e to the y is e to the y, but we have to use the chain rule. Okay. So this is where writing like this is definitely helpful. Okay. So if you want to use y prime, that's fine, but we could also just use dy dx. Okay. If you left the f of x there instead of changing to y, you could wrote f prime of x. Just don't forget the fact that, hey, y is a function itself. So I got to use the chain rule to say, hey, it's still going to be e to the y, but I got to deal with that. Now, as far as this is concerned, what we really like to see is I have dy dx. That's really what we're trying to find when we're trying to differentiate. Okay. With that said, the only thing I got to deal with is this piece here. What did we say e to the y equals, though? Not e to the y, but what did we say the other side was? What does this simplify to? Just x. So what does e to the y equal? No, just x. So this right here can be written as x times dy dx equal to 1. And if what we want is the derivative, right? All we have to do then is divide both sides by x. So dy dx would equal 1 over x. Which at that point, we just found that the derivative of the natural log of x is 1 over x. Now, what I hope you take from this is I used what we talked about last week, right? I used from my previous lesson the fact that we knew how to deal with the derivative of an exponential. The one thing, again, as we just talked about on the previous slide, always watch out for your chain rule. Okay, one thing we'll talk about in other sections is going to be called implicit differentiation. So anytime you have an output, a variable that does not represent the one you're differentiating with, okay, you always want to use the chain rule. But the nice thing here is we took a step in between and we used it to rewrite this problem to get rid of that e to the y, which allowed us to get to the derivative itself, right? So now we have the derivative of the natural log, and we didn't even have to do the limit definition because we could trust the limit definition that we already did. Everyone follow me on that? Now, some things definitely want to talk about so that we're paying attention to this. Why are we allowed to divide by x? Well, make sure you remember as you deal with the natural log of x, this comes from the inverse of an exponential. Okay, so if I do a quick sketch of the graph of an exponential, remember exponentials that we looked at look something like this. One side approached the horizontal asymptote, the other side grew infinitely, what we call exponential growth or decay. Whenever we deal with inverses, they're reflections over y equals x. So if I take this same graph, it's going to look something like this. This here, if this is e to the x, let me get rid of this part. If this is me just doing a quick sketch of e to the x, then this new graph is just a quick sketch of the natural log of x. Okay. What you'll find though, when we deal with this, is that the domain of this is 0 to infinity, where the range is all real numbers. So when I differentiate it, are we okay with dividing by x? Yeah, we're okay with dividing by x because the domain doesn't include 0. It's an open interval that starts at 0 but doesn't include 0. Now, the one thing we'll talk about though as we need will be like what's going on here, because when we deal with logarithms, you may remember you have a vertical asymptote. We looked at exponentials that had a horizontal asymptote. Well, logarithms, since they're inverses of that, have a vertical asymptote. Okay, but the main thing I wanted to make sure to show is don't forget that logarithms have a domain restriction. Must be a positive value. Any questions or concerns though before we go practice some of the derivatives? I got two new functions for us to differentiate. If I'm trying to find the derivative of this first one, do I need to worry about that -5? No, right? This is a situation where we can remember our properties, right? That says, hey, really, I can just multiply that to whatever I find. Okay. Just a constant multiple here. So make sure you see with this one, hey, the derivative of natural log, what did we just say it was? 1 over x. So -5 times 1 over x, or you can just write it as -5 over x. Okay. Now, one thing I do want to point out here is use your properties of logarithms. Technically, we could write this as x to the -5th as an exponent. So if we go back over there, anytime you have a constant multiple, it's not even on this list. But this is one of the properties of logarithms that, hey, these things actually have the same value as far as functions are concerned. Okay. It's the power property that we've learned about logarithms, which means if I differentiate this, what should I get? I better get the same thing, right? So let's check it just to be careful. What I hope that you see here is maybe sometimes you're using your properties can make something more straightforward or more involved. Okay. So as I do this one, are we good if I write that first? What do I need to multiply by though after I do that? Not 1. So I did the derivative of the natural log, right? 1 over whatever's on the inside is what we're going to find. So this time it's x -5, so I'm going to put that 1 over that. Okay. But remember, this is where the chain rule comes in. Well, the derivative of that, right? So if we do the derivative of that, it'd be -5x to the -6, right? Not necessarily looking the same right now. But this is where, hey, we could do a little simplification to kind of clean that up. The first thing you could see here, you could have just combined the exponents, but remember, negative exponents just means you can move from the bottom to the top. So if I move the x to the 6 down there, all of a sudden now we have x to the -5 and then x to +6. So remember, hey, that gives us just x. Now, what you'll find though is be prepared. The problem starts like this, and if you remember your properties, you can get it to work out a little bit nicer as you saw with this first part, okay? What's going on with this next one, then I have to be careful of. I got a 3x, right? So I'm gonna do a chain rule, so we're definitely gonna need to go back to what we just reviewed, right? So we're gonna need that here. What else is going on with this function? All right, an x squared, right? What's in between the x squared and the natural log? It's times, right? So we're gonna need to use which rule? Product rule again here, right? So make sure you see that, hey, as I deal with this, making sure I go through each piece. I definitely need the chain rule because of that 3x, right? We're gonna use the power rule because of the x squared. But those are being multiplied together, so I need to remember to use my product, okay? So with that said, what do I put first? You could do the 2x first, that's fine. What would you multiply the 2x with, though? Uh, ln 3x. What goes next? So you did the derivative the first times the second, right? Plus, then we just need to flip that. So since you did the x squared first, here we would need to do 1/3x times 3, and just don't forget, keep your x squared, okay? Now, you said 3/3x, that's perfectly fine. Nothing's wrong with writing it that way. What works nicely in that simplification, though? What goes away over here? The fraction does go away completely. Well, we can get rid of the threes, right? Make sure you see that. But what can we do with the x? So if you deal with that, remember again, just like we saw over here, don't forget the exponent properties, right? X squared over x is just x. So the fraction goes completely away. Kind of nice. Not always going to happen, but definitely something that can happen, right? As we saw even with this one that we did here in the corner, this doesn't look as nice. But make sure you see that, hey, I started with x negative fifth. It kind of worked out together as I went through that problem, okay? Now, the key to remember though here is if you choose to do the 2x first, make sure you don't change that natural log of 3x, right? Then whatever you do over here, you have to keep the x squared and then do the derivative of natural log of 3x, okay? Yeah, I normally just keep it as a consistent order, right? First times the derivative of the second plus second times the derivative of the first. We will find though it gives us the same thing just in reverse order. The good news is for product rules, since it's plus, we're fine. The quotient rule, you have to remember that it's low D high minus high D low. You don't want to flip those. Any questions or concerns with this one? Well, remember, -5 over here was just a constant multiple. So what would the derivative of -5 be? It'd be 0, right? So if you did that one, which there would be nothing wrong. If you got stuck and you weren't sure, just remember, hey, that equals 0. So technically, we would have plus 0 times the natural log of x, which means that's gone if you went through that process. So in a sense, we're always doing it, but we're just recognizing, hey, constant multiple derivative is 0, so I don't even need to bother with it, okay? Does that answer that question? Any other questions? Now, this is a special derivative you want to be comfortable with. It doesn't follow in some of the patterns we saw before, right? The power rule is nice because, hey, I bring down the exponent and I subtract one. I can use that with many different powers, even rational exponents, because I have square roots and stuff involved, okay? E to the x was kind of nice, but it's another one that's kind of out there because, hey, I just have to remember derivative of e to the x is itself. Just don't forget the chain rule. The natural log has a special 1 over whatever the argument is, whatever's in here, I'm doing 1 over that. Okay, so if we want to write an expanded form for natural log, just kind of express what we looked at here, we could say, hey, the natural log of anything, if we want to differentiate that, will equal 1 over whatever is on the inside times the derivative of that very thing. And just making sure to take account for that chain rule. And what I hope that you saw here by me doing this one from a different perspective, we got the same result, right? So it's definitely something that we could show works. All right, so let's go look at this one then. Who's excited for this? What are some things that someone's noticing here, though, as we prepare to try to work this out? Huh? There's a lot of composite stuff going on, so definitely gonna need the chain rule, right? That would be the thing. I haven't seen x squared mind. It's 3 inside a square root chain rule at some point. Okay, because of that. All of this, though, is a what? Quotient, right? So we're gonna need the quotient rule. But when I do the quotient rule, what am I gonna have to do with both the numerator and the denominator? At some point, we're gonna need to deal with that, right? Converting them. But make sure you see here for both those are both products, right? This would be a product rule embedded within a quotient rule. With chain rule, this would not be a fun derivative to work with, right? Well, guess what? When you have something like this where your main operations are multiplication and division, guess what we can take advantage of? Oh, hey, let's take this and write it as the natural log of both sides. Yeah, I'm not gonna say that you're gonna run into problems like this all the time. I just wanted to show you the advantage of having the natural log derivative and especially the properties that go with natural logs. Okay, so make sure you see all I'm doing is I'm just natural log both sides of my equation. The reason I want to do that though is so I can use properties here. With that said, before I jump into the properties completely, are we good with where I would get this from? Is there any concerns with x squared minus 3 with a 1/2 exponent, what I'm talking about there? Now, this one's gonna look a little bit different, but guess what? This is the same thing that we just saw before, but instead of 1/2, I should do 1/5. Okay, so one of the things that we need to be careful of with this here is remember that rational exponents are gonna help us in our derivatives, but it also helps us with logarithms as well. Okay. What you're gonna find here is, as far as setting up your logarithms, you wanna break it down as much as you can using the expanded forms. Some of you might remember college algebra having to expand or condense logarithms. Expanding logarithms are gonna help us with problems like this. It seems like it's a lot, well, hey, since it's just multiplication and division, except for the composite side of things, right? The things inside of it, I can break this down to say that the natural log of y equals 1/2 the natural log of x squared minus 3 plus the natural log 3x squared plus 1 minus 3x minus 1/5 the natural log of 7x squared. Make sure you see here what I did is I took each element that we had in here, all the factors that were a part of this, and I broke it down into 4 different terms. Okay. What you're seeing here as far as dealing with this is the product property of a logarithm. If you have multiplication, I can break it up into a sum of the individual factors. As far as the quotient property, just remember if something's in the denominator, it has a negative exponent. That's where the subtraction comes from. Okay. Now, which term looks different than the others when you look at this though? The negative 3x. Why did I just put 3x there? Technically, I should have had this, right? If we follow the pattern that we did with every other problem just now. But just remember, this would be that inverse property. Since it was e to the 3x, I can just put 3x here, just the exponent. But that's only because it's base e. If it was any other base, I wouldn't be able to do that. But because it's base e, we're good to go. Everyone follow me on that? Now, please understand, is this going to be every problem that you run into? No, but what I want you to see here is I just went from something where I would need the product rule, the quotient rule, and a chain rule on top of that. And now all I need is a chain rule, as long as I know how to take a derivative of a natural log. It will not necessarily look the same as what we would have got, but all that cleanup we would have had to done with all that embedded in one problem is made nicer this way. The one thing you have to be careful of though, when I go through here and I start differentiating both sides of this, I'm not doing the derivative of y, I'm doing the derivative of the natural log of y. So be careful to see here, this would be 1 over y times dy dx. So be careful with that when you choose to do something like this. What that means is at some point, I'm going to have to bring this back into the problem. Okay, because that is sitting right there. Now, with that said, hopefully what you'll see is I'm just going to go one term at a time. So what's the derivative of this? All right, well, remember for the natural log, I'm going to put 2 times x squared minus 3. I had a 1/2 out front, and I'm just going to take whatever it is and put it in the denominator. Okay, what's the derivative, though, of x squared minus 3? 2x, right? So technically, hey, this just is 2x. Well, one of the nice things about logarithm as you practice them, just kind of make things a little bit more condensed, is I could have just put the 2x up here because that's 1 anyways, right? Now remember, this 2 is coming from the fact that it was a square root to start with. By using the rational exponent, we can bring the exponent to the front of the logarithm. That's the one part we do like about that. Okay. Now, as far as the derivative of the logarithm, I brought that to the denominator and I multiplied by the derivative of that thing. Okay. So is everyone good with where I'm getting the 2x from before I move forward? All right. Because of that, I'm going to get this out of the way then, and we'll move to the next term. This one was just a factor, right? 3x squared plus 1. Well, make sure you see I'm going to do 1 over that times the derivative of that. What would y'all get for that derivative? Everyone's good with 6x here? All right. hopefully you're seeing I'm putting the numerator in blue just to show that I'm getting that from the chain rule, okay? Whenever we do this, I'm putting 1 over my argument, multiplying by the chain. That e to the 3x was kind of nice though, because as I go to this next step, I'm just gonna put -3. Okay. But then we get to this last one where I'm gonna have the 1 over 5 times 7x squared times the derivative of that, 7x squared. Are we good though if I put that as 14x? Now, with that said, okay, I'm gonna erase this last piece because we did the derivatives where the 14x came from. I differentiated this whole problem. Do I have the derivative though right now? No. What do I need to do to get the derivative? I got to multiply that y on both sides. Everyone see that? This is where we would have to then say, hey, I got to deal with this piece here. I'm going to go over here and multiply both sides of this equation by y. Just make sure you remember you got to keep parentheses around all that we just found. Okay. Does it look nice? No. Please understand it does not look nice. Simplify what you can is what I recommend. So like that first fraction here, I can just get rid of the twos. This last fraction here, hey, I know 7 goes into 14. So there's some things we can deal with. All right. But when it boils down to it, it's not going to look nice. X over x squared minus 3 plus 6x all over 3x squared plus 1 minus 3 minus 2x all over 5x squared, which actually we should just put 2 over 5x, sorry, times the very thing we started with. Okay, so let me give myself some room. Okay. To be honest with you, at this point, if you're just trying to find the derivative, just make sure you multiply both sides by y and stop. Don't bother going any further because at this point, what we found is exactly what we're looking for. I have the derivative of y at this step. Okay, the whole point of this problem, what I want you to see here is having that natural log took something that would have been several slides of work, not just one. I squeezed it in here, one, correct? But it would have had to been several slides. So would have done one product rule, a second product rule, and then brought all that back together for a quotient rule, and then clean all of that up. Okay, so this is a situation where the natural log, it didn't make it that much better. It's still pretty tedious, but it definitely took a lot away, is what I hope that you see. Okay. And we got to practice natural log 3 times as far as the derivative of a natural log function. Any questions or concerns I could help someone with, though, just kind of clear this up. Mhm.
The 3x squared, is that 11 or is it still going to be 3x squared plus?
It's supposed to be +1. I don't know why it's not letting me write that right now.
And then with the 2 over 5x.
Yeah, so make sure you see here, I said, hey, I know 7 goes into 14, so that's where the 2 comes from. And then we had 1x on top and 2 in the denominator. The 5 was just there because we were dealing with the 5th root to start with, okay? Now, if you wanted to compare this back to the other way, just know that you would probably have to distribute all this through there, find a common denominator to get to a single fraction. It would not be something we want to do. But make sure the key thing I want you to take from this problem is be comfortable with your log properties. That's going to help you, okay? And we have to know where each of these is coming from when it deals with the derivative of the log. Now, make sure you remember the first time I wrote each of those out, though, I wrote it out using the chain rule. We just condensed it to make it fit one slide, okay? With that, we're at